And this time I end up with a negative 10. And so a negative 10 over a 30 is negative 1/3. And my units would be meters per second squared again. But I do get something a little different than over here. See, because this would say that the acceleration is in this direction, whereas this result would say the acceleration is in this direction, the negative direction. And so, again, knowing what direction the forces is makes a difference. It then results in what direction is the acceleration. And remember, that's important, because if the acceleration is in the direction the cart is moving, it goes faster. But if the acceleration is opposite, then it would be going slower. Now, this cart, you're probably imagining it being stationary when my friend and I start pushing. But let's imagine it was already moving. And so if it was already moving and my friend and I come over here, and if I take scenario way back here, number 1, and both of us push in the positive direction so that our net force is 70, and so our acceleration is 2.33, and it's to the right, and it was already moving to the right, then I would say that the acceleration and the motion are in the same direction, and this cart then would go faster. But if my friend and I did this, and it was already moving, simply put, I would be pushing in the direction it's moving, but my friend would be opposing that. My friend would be pulling it backwards. We get a much smaller acceleration, but we do get a positive acceleration. In other words, the acceleration is still in the direction that it is moving, and so it would still go faster. Now, although its rate of going faster would be much less than the rate of going faster here. But it would still go faster. That's just a long way of saying I'm, pushing it forward more than my friend is pulling it back. But this one tells me yet a different story. All right, this one tells me that if it was already moving to the right, and I start pushing it this way at 30, but my friend pulls it at 40, and in a sense you could say my friend's doing more than me, I get a negative acceleration. And so the acceleration is this way, and it's moving that way, and what would happen is it would begin to slow down. And I suppose eventually it would come to a stop. And if we kept doing it, then my friend would start pulling it the other direction, and it would start going faster in the other direction. But just that initial part where it's going this way, but the acceleration is negative, it would begin to slow down. And so, again, notice that I'm just using some numbers and trying to teach you here what is Newton's second law. And Newton's second law says net force. That's crucial, net force. Because to get net force, you have to put the forces together. So you have to look at how many forces do you have. Now, I've been showing you with 2, but I think you can see that this would also work for 3 or 4. But you also have to look at direction. Well, let me do one more before we move on to Newton's third law. But this might be the hardest one yet. What if I have this? And to imagine this, you might have to picture yourself up on the ceiling looking down, because I'm going to push still with my 40 to the west. So I'll do this, 40 to the west. But my friend stands here and pushes with 30 to the north. And so I'll say that way. And so I know that the way the geography of this building's laid out doesn't match a typical compass rose. So this is north and this is west, where a typical compass rose, that's north and that's east. But that aside, here's my question. what is the acceleration? Well, the easy part is the mass. It's still 30 kilograms. Remember, the mass was a scalar. It's a number. Hey, it doesn't change. Doesn't matter which way you push or pull, or that has nothing to do with it. Those are forces. The mass is just a number. Okay, so I've got the number. There's the 30. But what is the net force? And I think the best way to see this is to step away from forces and go to distance. What if I were over here and I said take, and I'll just simplify it a little bit and say 4 steps, turn 90 degrees, and take 3 more steps. So in this room, I might start here. What if I was here and I said take 4 steps? 1, 2, 3, 4. Okay? Turn 90 degrees and take 3 steps. 1, 2, 3. So that's a combination of a 4 and a 3. What is that equal to? And so you can kind of see that the 2 of these would be the equivalent of what would be the hypotenuse on a triangle. And so it would be angled like that. And so now I'm going to take you back to your math class. How do you get the hypotenuse of a triangle? And you probably know this as Pythagorean's theorem, that in verbal form says the sum of the square of the legs equals the square of the hypotenuse. A squared plus b squared equals c squared is how you'd write it in a mathematical formula. In words, that would mean the sum of the square of the legs, so that's this, equals the square of the hypotenuse. And so that's exactly what I'm going to do. It's not so obvious how to do this one because it's not a simple plus or minus. It's got a 90-degree angle to it. And I picked this one because this is one of the magical triangles that you may have remembered. The 3, 4, 5 right triangle is the one of the what we call the magical triangles that can be labeled with the integers. That is, if you take the 3 squared, you take the 4 squared, you will get 5 squared. And you can see that when you take the 9 and the 16 and you add it together, and yes, 25 does match 25. So what I would say here is that I'm pushing with 40 to the west. My friend is pushing with 30 to the north to figure out what is the, and here's a key word, result of these two forces. Okay, what are these two equivalent to? Do I add them? Do I subtract them? And in this case, it's neither. In fact, a fancy math term is we like to say you are going to combine them in quadrature. Forget the fancy word. But what we're going to do is figure out it's the length of the hypotenuse. We have to do Pythagorean's theorem here. Now, I picked the 3, 4, 5 here because if I just multiplied everything by 10, I would have a 40, 30, 50 triangle, and that's what I have here. I have 40 to the west, I have 30 to the north, so that means across the hypotenuse would be 50. And so you can see why I did this one last, and you can also see why I said this is probably the hardest of them. Because to say this verbally can be confusing. You take two forces. What is the result when you combine a 40 and a 30? You get 50? I mean, if you told a third grader that if you put 40 and 30 together, you get 50, they're going to go, you're crazy. You put a 30 and a 40 together, you get 70. Or maybe if you want to subtract them, you'll get 10. But you're never going to get a 50, and that's just not true. When the direction is involved, when it's two-dimensional, you'll get a 50. All right, so all that is to say that I need to get this net force, which means I have to combine the two forces together, and how I combine them could be adding them, as I did here, could be subtracting them, as I did here, or it could be putting them together in quadrature, or putting them together with Pythagorean's theorem because they're at right angles with each other, and that's what I've done here. So 50 divided by 30 goes what? 1 2/3. And so this would be the acceleration. Now there's another even harder question we could ask. What direction would this be? Now, to answer that, we have to know some mathematics called trigonometry. And that's where we're going to stop for this class. This class is not required that you know trigonometry. Many of you are currently enrolled or soon will be enrolled in trigonometry. So if you know some trigonometry, you will recognize that this would easily be calculated with what we call the arctangent to figure out that angle. And so those of you with a little more math, I'll just say this is roughly 37 degrees, and you can work it out. But for those of you who don't, let me just say, that's okay. You don't need to for this class. Now, for the next class, that's different. The next class, you're expected to already have completed both trigonometry and calculus. So we'll continue this at the next level. What I want from you guys then is just to be able to draw a picture and get an idea. Okay? That what direction would it be? Well, it wouldn't be just west. And it wouldn't be just north. You might say it would be kind of this northwest direction. But northwest usually means 45 degrees. Now, 45 degrees, even if you haven't had trigonometry, you know you would get 45 degrees with an isosceles right triangle. And so this would have to be 40, and then that would have to match it with 40 to get an angle of 45 degrees. And so that's what you know from your geometry. And all of you know that, or at least I will remind you from your geometry, you know that. So again, you don't have to know your trigonometry to get this angle at 37 degrees. But here's what I do expect. I do expect for you to be able to say that the direction it goes is not west, is not north. It's not even northwest by 45. It's a little less than that. And so, again, the exact number is not as important as just drawing the pictures and using what you do know from your drawings and your geometry, that this angle is something less than 45. Okay? Or let me try this one. Because here's one that I believe shows up on your homework. And it says something like this. It says, what if an airplane is flying at 100 kilometers per hour, and as it's flying, there's a crosswind? Now, one of the reasons I want to bring this up, because in the past I've had students go, what is the word crosswind? Okay, so crosswind means hitting it at a right angle. All right. And so the wind blows the plane, and they say it's a hurricane. So the wind is really strong at also 100 kilometers per hour. And then they ask, what is the speed of the airplane and the direction? And let me start with the direction because that's what I was focusing on. This one, even if you don't know any trigonometry, what do you recognize right away with this triangle? And I hope we're back to here. Right? This is the isosceles right triangle. And so that angle would be 45 degrees. That's one of the special triangles. And so your two special ones are your 45, 45, 90 and your 30, 60, 90. And your other special ones are the magical triangles that have this ratio of, the 3, 4, 5 right triangle. And later on I'll use another magical triangle, so keep in mind the 5, 12, 13 triangle. Okay. But this then, I could either use Pythagorean's theorem or remember from my trigonometry is root 2 times 100. And so that's 141 roughly kilometers per hour. And so I hope I didn't give too much away, but that in the past has been a little challenging ones, and so I just thought I'd throw that one out there. But it fits in perfect with this discussion I'm trying to get across here with Newton's laws of motion, that, again, the second law can be a bit of a challenging one because it's a calculation. I might say then it's probably the most used one because it gives us a calculation, it gives us some numbers. But the trickiest part of this is getting this number. What is the net force? And keeping in mind that this net force is not the force from just one person. The net force is the result of the two people. And so I don't want to say that there's three forces here, but I want to say that there's three things you should keep in mind. There's a force from person 1, me, there's a force from person 2, my friend, and then there is the combination or the resulting force of us together. What are we equivalent to? And that's what the net force is. So the net force isn't a real force. It is the result of all of those. Again, just like if I can go back to my silly example, you might have multiple jobs and maybe you make $100 this month groceries. Bagging groceries at the grocery store. I think that's still open. I'm trying to look for jobs that are still open. And maybe you lost your job. Maybe you were bartending and you now have unemployment. Okay, so you get say 200 from unemployment. You get 100 from bagging the groceries. At the end of the month, you would say, I made $300. But again, you didn't make $300 from any one job. 300 is the total of those two. So you got two jobs, but there's three numbers you keep in mind. It's the money I made from job 1, the money I made from job 2, and then the result of those. And that's what I mean here. And you'll see that on the homework. Sometimes students will sit down and they'll do a calculation and they'll get the net force and they'll stop right there and they'll go, oh, I got the net force. Oh, that's the force from person 1. No. And then they'll go, oh, well, that's the force from person 2. No. This is the net force. This is not saying how much from person 1 or from person 2. This is saying how much is the combination of those. And so keep that in mind. That's probably the most common mistake on the homework is student kind of stops. The question says, hey, how much force is coming from person 1? And then they do a quick calculation here because the problem gives them mass and acceleration, and then they get net force and they stop and they go, okay, I got it. No, you're not done. All you've done is figured out the net force from the two people. You still have more to do in that problem. You only did half of it. And so it's kind of my little warning for you, both on the homework and then on the test. Don't stop there. Once you get the net force, then you might have to go, okay, well, the net force came out to be 10, and they want to know this force, but this one's a 30, so that one must be 40, and so you can continue to work on the problem. All right, well, I probably spent too much time there mentioning the second law, but I think that's the harder of the one. So let's move to the third law, and let me say it again. The beauty of physics is that these three laws are fundamental to all motion. And so even though I'm using little carts up here, hopefully what you get out of this is this could be a bus, this could be a plane, this could be an asteroid, this could be a nitrogen molecule. It doesn't matter what the object is, these all follow these three laws. And so as we study them, we like to say that, it's just a few simple principles explain a universe of phenomenon, and that's why we, start off with these simple things like carts and little objects I can roll across the table, but it is not an elementary idea. This is a big idea. It can explain all motion. All right. Well, let's do the third law here. The third law is a little different than the other two. It's just as important, and so we have to always keep it in mind. But this one involves two objects, whereas the first and the second law kind of went together, and they were only worried about one object. Oh, watch. Let me put it on the board here first. It says if an object, and so maybe I'll call that object 1. So here we have object 1. So if an object exerts a force on a second object. Okay? So again, let me stop right there. And this is what I meant by the third law is a little different. We've got two objects involved here. All right, so for me, maybe I'll do something like this. Maybe I'll come along and say, all right, I have my first object. I'll make it this little cart. And then I'll make a second object, and so I'll make a cart number 2. And this first part of the sentence is saying, if an object exerts a force on a second object. So if number 1 puts a force on number 2. So maybe I'll just put a little arrowhead. So maybe number 1 crashes into number 2. And so I'll just say F for force. So number 1 is putting a force onto number 2. That's what this said. So if an object exerts a force on a second object, comma, the second object then exerts an equal force back on the first object. So in my picture, I guess it would look like this, that, okay, 1 collides into 2 and is putting a force on it. And during that collision, then 2 would put a force on 1. We like to call this law the action-reaction law. Because these two objects, each of them have a force on them. And the force is actually equal in magnitude. Opposite in direction, but equal in magnitude. So you can't have just one force. You always have two. But, however, be careful here. They're on different objects. See, when somebody were to say you have two forces that are equal and opposite, if you were to add those together, you would say the net force is 0. Okay. But you would also only add them together if they were on the same object. And that's a common mistake that the beginning students make. They want to say, okay, let's look at the net force. And they want to add these two forces together. Don't do that, right? These are two different objects. This would be, again, like saying, here is student 1, here is student 2. And if I use the silly example that forces kind of represent your income, I wouldn't, add the income from that student and then add the student of that student together and combine them in some way. These are individual students. And so this is your income. And then this is your income. And so this is where the third law, I think, trips up students, is they are so busy still thinking about the second law and adding up all the forces, and they see these two forces and they want to add them together. And then they realize, well, the third law says they're equal and opposite, and so if they're equal and opposite, you get zero. And so there's no acceleration. And that is not at all what this is saying. You don't add these forces together. You only add the forces on that object. So in other words, if and I'll change some color here, if I wanted to know what's going to happen to cart number 2, let me circle cart number 2, I would add up all the forces on cart number 2. And if I want to know what happens to cart number 1, I'll circle cart number 1, I would add up all the forces on cart number 1. But I would never add the forces on cart number 1 and cart number 2. And so I want to emphasize, I am not going to say this scenario gives me a zero acceleration. In fact, I'll even show you this scenario. Right? This scenario would look a little bit like this. And maybe to match my picture, I'll do this. I'll call this cart number 1, and here's cart number 2. And so if cart number 1 comes along and then hits cart number 2, did you see what happened? I mean, let's talk about this, right? This is a really good, let me get a little closer here. But this is a really good indication of showing that they're on different objects. See, here's cart 1, and it put a force on cart 2, right? It put a force on cart 2 that way. Cart 2 accelerated that way. But at the same time, while cart 1 is putting a force on cart 2, making it go that way, cart 2 is putting a force back on cart 1, and therefore making an acceleration on cart 1 that way. And of course, remember, cart 1's going this way. So the acceleration and the direction are opposite, and so cart number 1 would be slowing down. And that's exactly what we see. And so let me emphasize, I don't add the two together and say I have zero acceleration. No, I do have an acceleration of cart number 1. The acceleration of cart number 1 is this way, but it's moving that way, so it slows down. Cart number 2 has an acceleration that way, and of course it's also moving that way, so it speeds up. And sure enough, there it is. Cart 1 hits cart 2. Now, in this case, the two carts also have the same mass. See, look closely at this third law. It says in words here, and hopefully in pictures here, that the forces are the same. Period. Does it matter how fast the carts are moving? No. Does it matter how much mass they have? No. Does it matter what color the carts are? No. Does it matter what time of day? No. None of that matters. You can see it here. If I put more mass on this one and I collide it into it, watch the first collision. There it puts a force on that one. But it also puts a force on this one. And I'm claiming that those two forces are equal. Notice, though, they don't have the same acceleration this time. See, watch. Without this first one stops and makes the second one go. So there they have the same acceleration. And I guess here's what I'm trying to say. When I come over here to figure out the acceleration of number 1, I would say the acceleration of number 1 is the force divided by mass of number 1. When I come over here to try to figure out the acceleration of number 2, I would say the acceleration of number 2 is the same force, but maybe not the same mass. And so let me emphasize, the third law is actually a lot simpler than students usually make it. They want to say, whoa, 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 they got different accelerations, and that's true. So then the students want to say they have different forces, and no, that is not true. They do have the same force. They may or may not have the same acceleration because it depends on their same mass. Watch, I think you can see it better if I do it this way. Let me take this cart, let me turn it around. Let me put them together so neither one is moving. And when I release the plunger, notice how they both go out, right? If we call this cart 1 is then pushing on cart 2, but also cart 2 is pushing on number 1. And the third law is saying that the force is the same. The second law then goes on to say that the accelerations could be the same if their mass is the same. And so these two carts have, they're identical carts, and they have then the same mass, or at least nearly the same mass. And so when I release them, you can see that they go out with the same acceleration. But watch this. If I take this cart and I close it up, and maybe I put more mass on this one. And so now cart 2 has 3 times the mass of that one. They don't have the same acceleration. But they do have the same force. Are you catching that difference? And so watch what happens when I release the plunger here. See how much more acceleration that one has compared to that one. And I want to say it again. In that case, number 1 has more acceleration, not because it has more force, but because it has less mass. And so Newton's third law, keep in mind, says the forces are equal. Period. End of story. What if they're going fast? Doesn't matter. What if they're going slow? Doesn't matter. What if one is red and one is blue? Doesn't matter. What if it's on Tuesday? Doesn't matter. What if it's early in the morning? Doesn't matter. The forces are equal. And so that law sounds simple on the surface, and I hope you'll see it that way. It really is equal forces. And I know sometimes that's hard to imagine. I mean, in your mind, you're probably thinking, wow, what if I had this giant 18-wheeler Mack truck going down the freeway, and this little tiny Volkswagen runs head into it? Whoa. People in the little Volkswagen are probably going to die. And the people in the truck might just get a little whiplash and say, whoa, did we hit something? And you might say, oh, the forces were different. No, the forces weren't different. This big truck coming towards this little car, slamming together, the force on the car is the same as the force on the truck. The force from number 1 onto number 2 is exactly the same as number 2 onto number 1. However, that doesn't mean the accelerations are the same. In fact, we can see that the lighter mass one has a greater acceleration. So what ends up happening is the little Volkswagen has such an acceleration, it comes to a stop, turns around, and starts going the other direction as the truck just keeps kind of plowing through. So the truck has very, very little acceleration. But it's because it has a different mass, not because it has a different force. Well, I've got some other, I think, cool ones to kind of show you Newton's third law. This right here is a little prop. If I spin it here, You can see the motor, and there's some batteries underneath here, but the motor spins the prop. And this is a good example of how does an airplane work, at least a prop airplane. It would also be for a boat, the prop on a boat. What makes it go forward? Watch, I can put it here, and if I turn it on and let it go, well, you'll see it begins to accelerate. And in this case, it accelerates to your right. And so as it accelerates to the right, well, that means there must have been a force on it. Where did that force come from? How did this thing even work? Remember, this chapter is talking about explaining the motion. And the answer is simply this. As the prop spins around, it pushes on the air. So if it pushes on the air, what does the air do? Pushes back on the cart. And so the air gets pushed that way, and the cart gets pushed the other direction. How does the force on the air compare to the force on the cart? And I hope some of you at home are saying, they're the same? Yes, they are the same. The force on the air that way is the same as the force on the cart that way. Now, notice I'm not saying they have the same acceleration. In fact, the air has a lot less mass, so the air goes a lot more, or has a lot more acceleration than the cart. But the force is exactly the same. The force on the air is equal to the force on the cart. Because the air puts the force on the cart, and the cart puts the force on the air. Third law, equal and opposite. Maybe you could see it a little bit better because it's hard to see the air with this one. So I brought this one, which we call the rocket cart, because it leads to a very important question about airplanes. So can airplanes with props, or jet for that matter, be used in outer space? No. Why not? Again, because the